Hi, Michael Sankner here, Thinking Skills Dojo. What logic looks like. This is the basic vocabulary and concepts to understand logic as it's used in writing. Okay, so here are the concepts. By the end of the presentation, you should have a good sense of what all these words mean because they're very useful later on when we're talking about making arguments, for example, for writing. We're going to start with some geometry because that's how logic actually got going. Let's start in ancient Egypt. Here's a photograph taken 2,500 years ago in Egypt. Well, no, okay. It's probably more like a painting from the 19th century. And as you can see, the weird thing is, what's up with all that water? Isn't that the desert? Well, the thing is that every year the Nile River would flood, which was great. It irrigated the country and the crops would grow. But the downside was that the water would wash away all the markers for the fields, and then they wouldn't know whose field was whose. So this really bad drawing gives you the idea that there are these guys, probably slaves, and they would go out into the fields with ropes and make triangles. What kind of triangles, you ask? Well, they used the famous 3-4-5 triangle. You'll notice on the top there's 3 sections, on the side there's 4 sections, and on the diagonal there's 5 sections. And what's special about this is that in the 3-4-5 triangle, one of the corners will be a square corner, a right angle. So the rope stretchers use that fact to make rectangles in the fields. They'd map out one triangle like this. I guess they would pound stakes in at the corners and mark it off. And then they would make another triangle like that, and then they'd have a rectangle. And then they'd add another rectangle and as many rectangles as they needed to mark off however much land they wanted to. So our first concept is proving something with facts. So facts, you could say, are physical, like those ropes. What is a fact? Well, here's my definition. Something that can be considered true because it happened or can be observed. And you could almost add, in the world that we live in, because there are people out there saying there's no such thing as facts. And maybe on some other world that's true, but on this world, when you look around, yeah, there's such a thing as facts. For example, it is a fact that the Egyptians used ropes to measure land. And the evidence is these paintings from that time that show the rope stretchers going out to do their work. Probably pretty hot work, I think. Now let's fast forward a few thousand years to the time of the ancient Greeks. Here's a picture of some Greeks doing geometry, which they did just to practice thinking. And at a certain point, people started to wonder, well, what would happen if you made squares around this 3-4-5 triangle, where the length of the side of each square is the same as the length of the side of that triangle, which would look like this. And this is a cleaned up version of that. And somebody realized, oh, with this 3-4-5 triangle, the green amount is equal to the blue amount plus the red amount, which you'll probably recognize as the famous equation a squared plus b squared equals c squared. Let's imagine it as cake. What this would mean is like the big cake would have exactly the same number of mouthfuls as the medium-sized cake plus the smaller cake. And the kids would be screaming, how do you know that's true? Which leads us into the concept of measurement. Measurement means you're counting something. Here's my definition. Measurement is a form of proof that uses counting. So in the case of the 3-4-5 triangle, it's very easy. As you can see, 9 squares plus 16 squares equals 25 squares. It's the same amount of cake. So that's the form of proof called measurement. Now, logical argument is different because it doesn't use any counting or measurement. Let's start with the word logic. The word logic comes from the Greek word logos, and that was the word for speech or word. So the Greeks used words to go through the logic. That's why it's called an argument. They didn't really write it down that much. They would say it out loud, and that's actually still a really good way to do math or to work through the logic of your essay. Say it out loud. These arguments were more like a conversation. So you'd say something like, well, let's say, imagine you've got 3 squares surrounding a triangle. And I say, yeah, okay, I can imagine that. And you say, well, imagine it's a right triangle. And I say, oh, okay, yeah, I'm with you. I'm imagining that. And I'd say, and you'd say, well, here's my point. And I'd say, wow. Now, this isn't finished yet because you haven't proved anything. But my point here is that that's more or less how an argument is structured. We organize the logic in this series of statements to make a point. And that's what logic looks like. We'll say more about the believing part in a minute. By the way, this particular argument is also a kind of principle. What's a principle, you ask? Principles are also part of logic. Principles are like laws of nature. My definition is a principle is something that's always true in the world that we live in. So for example, water in a container freezes when you chill it. Balance is important. Choices have consequences. Those are principles. Maybe in some other world those things aren't necessarily true, but in this world those things are always going to be true. And this is important because there are people out there saying basically principles are not real, but actually principles are real if you just think about it. So far we've just been talking about proving using measurement, but proving with logic is different. That involves using premises and conclusions. So let's prove something now with logic. Okay, so let's say you ask, we know that if this was a 3, 4, 5 triangle, the amount of blue cake would be equal to the amount of the 2 red cakes. But would that be true in all cases? Is it true in this case? Because although it's a right triangle, you can see it's not a 3, 4, 5 triangle. It's some other random proportion. So is that still true? Well, it turns out the Greek philosophers came up with a way to prove that, yes, it's still true that the blue cake is equal to the red cake. Oops, probably wasn't that philosopher. Probably more like this philosopher. Anyway, here's what they did. They used a larger box. Okay, so how does that work? You draw a larger box and you put the squares in it like this. So put the red squares in it. Draw a larger box and then put the blue square in it. Then you compare the two larger boxes. And as you can see, the larger boxes are the same size, and each box has squares in it, and each box also has 4 white triangles, and the triangles are all the same size. So the argument in words would look something like this. You'd say, okay, the area of the large box is the same as the area of the red squares plus 4 triangles, and the area of the large box is also the same as the blue square and 4 triangles. And since the triangles are all the same size, and there's the same number of triangles in each box, they take up the same amount of space, so we can just ignore those, or as we say, factor those out. And therefore, the blue square and the red squares take up exactly the same amount of space, which is interesting because when you look at it, the triangles especially, they look bigger on the right, to me at least, but they're actually the same size. They're just arranged differently. This works for any right triangle. By the way, I'm attaching a paper version of this that you can actually print off and cut out and play with. And it's fun because it doesn't look like they're going to be exactly the same size, but it totally is exactly the same size. I tried this like 100 times when I found out about it. So that was proving something with no measuring, right? Only logic, which leads to the idea of generalizing. When you're hearing arguments, you might hear this expression, you can generalize or you can't generalize. So what does that mean? It means you've got an example or you've got 2 examples and then you're making a general rule out of that. Sometimes that's appropriate and sometimes not. For example, this apple's red, this apple's red. So therefore, apples are all red, right? Which we know is not true. So sometimes it's valid and sometimes it's not. This generalization is pretty much true, right? Soccer players kick soccer balls. But what if we say soccer players are athletic? Is that true? Well, some are. Probably most are. But not all soccer players probably are athletic, right? And saying a person is a certain way based on what group they're in, logically speaking, we can see that's overgeneralizing. And this happens a lot these days. Okay, we're getting to the home stretch here, and we're getting into some logical argument that has something called premises and conclusions. Premises are presented as being true. That's the, well, let's say blah, blah, blah part, right? Premises support a conclusion. That's the which would show blah, blah, blah part. Premise helps make the point. And conclusions are the end point of the argument. It's kind of like the punchline. And the conclusions follow from the premises. So let's see an example. We said that premises are presented as being true. So for example, in the case of the 3, 4, 5 triangle, we're saying that the corner of that triangle is square. That's one of the premises. So we're saying that it's true that the corner is square. And what if the premise isn't actually true? For example, if the triangle isn't a right triangle? I redrew this one a little to make the corner not square anymore. See that black line there? So now it'll be bigger than the blue square plus the red square, which haven't changed size. So the whole thing doesn't work anymore, right? If that triangle is not a right triangle. Meaning, if the premise is not actually true, then the conclusion is not valid anymore. So premises support the conclusion. Okay, we also said that premises support the conclusion. Here's an example of that. If we say plants should be watered every day, we come to one conclusion. Right? You're looking at that plant and you're going, oh, the poor thing, it needs water. But if you say plants are sensitive to being watered every day, you might come to a different conclusion. You might say, no, that plant should not be watered today. So what do we do with premises and conclusions? We build arguments. The logical argument is a collection of premises and conclusions that all fit together in kind of a chain, right? Let's look at that. We'll go back to the same example of squares and triangles. Okay, here's the whole argument. I'm not going to read it all right now, but just notice a couple of things about it. First, notice that each sentence is true, right? Computer programs are like this. Each sentence has to be true or it won't work. And if any of these sentences isn't true, you get the famous bug. Program doesn't work. And same with your logical argument. Now notice that the argument starts with some premises and they lead to conclusion 1 and 2. And then there are more premises. The argument continues. Then there are more conclusions. And that's how the argument develops. And the last thing to notice how the conclusion from the earlier part of the argument gets used as a premise in the later part of the argument. And that's how arguments get built up. Now, speaking of premises and conclusions, sometimes you hear this phrase, my logic and your logic. And that's not actually a thing, okay? When people say my logic, what they actually mean is my premises and conclusions. And when they say your logic, they mean your premises and conclusions, which also could be valid or invalid. So when you hear or read an argument, you've got to ask yourself, what are the premises? Are they true? What is the conclusion? Does it actually follow from the premises? And if the answer to any of these questions is no, then that argument is not valid. Okay, summing up. In this presentation, we looked at arguments and we said that they are made of premises and conclusions, and that arguments can be either true or untrue, basically because premises can be true or untrue and conclusions can be true or untrue also. And we looked at generalizing and we said that's also either valid or invalid. And we said that the argument is only valid if both the premises and the conclusions are valid. And then on the proof side, we said that there's the physical, concrete kind of proof, which is facts and measurement. And on the mental or abstract side, there's logical argument as proof. And we said that all these concepts apply to arguments that are also written or spoken. And these are the basic ideas of logical argumentation. If you have any questions or comments, get in touch. Thanks, and talk to you soon.